Now we can see this problem number 9. A beam is simply supported and carrying a uniformly distributed load of 40 kN per meter run over the whole span. The section of the beam is rectangular, having depth as 500 mm. If the maximum stress in the material of the beam is 120 Newton per mm square, and moment of inertia of the section is 7 into 10 power 8 mm power 4, find the span of the beam. You have to find the span, length of the beam here. Okay. So length, you need to find out the length. Here uniformly distributed load W given 40 kilonewton per meter and depth D given 500 mm and maximum stress sigma maximum given 120 Newton per mm square and moment of inertia of the section I given 7 into 10 power 8 mm power 4. They are asking length. You need to find out the length of the beam. So section modulus for maximum bending moment M is equal to sigma maximum to Z. That equation you know. So here you need to find out the Z value, section modulus, that is I by Y maximum. So I is nothing but moment of inertia given on the problem 7 into 10 power 8 and Y maximum is nothing but D by 2. So total 500 mm D. So D by 2 means 250 mm. So 500 by 2, 250 mm Y maximum. So I 7 into 10 power 8 given, Y maximum 250, you can find out Z value 28 into 10 power 5 mm cube. Now, this is the maximum bending moment for simply supported beam carrying uniformly distributed load, therefore M is equal to WL square by 8. Right? So W value is given 40,000. Right? I can see here the W is 40,000 Newton per meter, 40 kilonewton per meter, therefore 40,000 Newton per meter. Therefore, into L square divided by 8. Here M is equal to 5000 L square into 1000 Newton mm, converted to Newton meter, Newton mm, 10 power 3. So the formula is M is equal to sigma maximum into Z. So M value, you know, 5000 L square into 1000 equal to sigma maximum given in the problem 120. And Z you found I by Y 28 into 10 power 5. So here L square equal to this much. And L is equal to 8.2 meter. Your unknown value is L. Therefore, you can find out the L value as 8.2 meter. So simply supported beam length is 8.2 meter. So you have to calculate the length. And you can see this problem. A timber beam of rectangular section of length 8 meter is simply supported. The beam carries a UDL W 12 kN per meter run over the entire length and the point load 10 kN at 3 meter from the left support. You can see that simply supported beam 8 meter length, uniformly distributed over 12 kN per meter over the entire length. 10 kN is acting at the 3 meter from the point A. Okay. If the depth is 2 times the width, if the depth is 2 times the width, okay, if D is equal to 2 times B, and the stress in the timber is not to exceed sigma maximum is 8 Newton per mm square. So find the suitable dimension of the beam. That is breadth and depth they are asking. If the depth T is equal to 2 times breadth, what is the breadth and what is the depth that we have to find. Okay. So what we have to do, let breadth of the beam will be B. Okay. Solution. The section modulus for maximum bending M is equal to sigma maximum into Z. So here first calculate the section where bending moment is maximum, right? So this is not a simply supported beam subjected to UDL to get the maximum bending center. Here this simply supported beam is eccentric load. Okay, it's not exactly at 4 meter. It is 3 meter distance from the A. Therefore, it is the unsymmetrical loading, right? Unsymmetrical loading. So therefore, you need to find out the maximum bending moment value. And where the bending moment is maximum, the shear force will be 0. So now the equation of pure bending can be used. So for doing this, first calculate the reactions. You need to find out RA and RB, then shear force value, then where the shear force value will be 0, there you will get the maximum bending moment. So at that point, you can find out the maximum bending moment, M maximum, sigma maximum given, right? So Z equal to BD square by 6. In that, the B value, D value, unknown value, you can get. So here calculate the support reaction. This and all you know already. Sum of the upward force equal to sum of the vertical force. Take moment at A equal to 0. Then you will get the RB value. Then substitute in this equation RB value. Then you will get the RA value. So reaction. How to calculate the reaction? You know very well. Then shear force. How to calculate shear force? In the second unit, we already we learned how to calculate the shear force value. So shear force means here you have to take the section. Suppose you want to calculate the shear force between A and C, you have to take the section between A and C. You add all the forces. Suppose here what is the forces are there? UDL and these reactions. So at the point A, the shear force will be RA value. At point C, left side, the shear force will be this value of RA plus RA, then minus this 12 into 1000 into this 3. So like that you have to calculate shear force values and all. So that also you know how to calculate. Here FA means nothing but RA 54,250. Then next left hand side RA minus 12,000 into 3, like that. You have to calculate the shear force value, and you can see here the diagram will be like this. So at particular point the shear force value will be 0. So in that equation you substitute, then you will get the x value, okay, from here to here 0.87 meter x value. Okay, so how to calculate x value means equation. In this equation, if you substitute, you will get the x value. If you want to, one more, if you want to explain, I will explain shear force, how to calculate the shear force. So to calculate the shear force value, what you have to do? We have to first to use two equations. One is sum of the moment at A equal to 0, and another equation is sum of the vertical force is equal to sum of the horizontal force. Now sum of the moment at A is equal to 0, suppose. Then here RB into this distance minus RB into 8, then plus 10 into 3, then plus 12 into 1000 into this value 12 into 1000 acting center into this 8 into this distance is 8 by 2 and will be equal to 0. Let's see here RB into 8 minus 12,000 into 8 into 8 by 2 minus 10,000 equal to 0. Then from this you will calculate the RB value. Then this RB value, if you substitute here, sum of the upward force RA plus RB equal to sum of the downward force. Downward force is nothing but 12,000 into 8 plus 10,000, isn't it? Downward force. 12,000 acting downward. 12 into 12 kilonewtons, so 12,000 Newton per meter acting downward. UDL converted to point load acting at center, 12,000 into 8. Then plus this 10,000 Newton, kilonewton, so Newton, 10,000 Newton. So 12,000 into 8 plus 10,000 is acting downward. Okay, na? So RA plus RB is equal to 12,000 into 8 plus 10,000. So in this value, if you substitute RB value, you will get the RA value. So RA, RB we have calculated. Then this RA value is nothing but shear force at A, that is 54,250 here. So here RA value is 54,180. Therefore, you will diagram 54,250 RA value. Then because of this UDL, this will be linear like this. So how can you calculate? Can say shear force at C1, that is LHS side, FC1. Can say F shear force at C1, suppose LHS side, how much value you have to find. So left hand side, if you consider FC1 is equal to RA, sum of the upward force, shear force, RA, then downward force is, you can see here, this 12,000 acting here, UDL, therefore this minus downward acting 12,000, therefore minus 12,000. So plus 54,250 minus 12,000. Okay, this into 3. If you convert this minus 12,000 UDL into point load, this UDL into 3. So minus 12,000 into 3 becomes point load. Okay, so at section C, FC1, that is section C, left side, left hand side, this force and this UDL force converted to point load. These two forces are there. This upward positive 54,250 and downward minus 12,000 into 3. Then how much you get? 18,250 Newton. So here diagram 18,250 here. Here you can see 18,250. So from the 54,250 it is reduced to 18,250. Okay now. Okay, so from the bottom it is okay 18,250. Then right side, this section FC, right side if you take, you have to add this force because of this force. How much? Again this 18,250 because of this downward minus 10,000. So 18,250 minus 10,000, 8,250. So from this value, this is value of 18,250. From this it is reduced to 8,250. Okay. Then between C and B, okay, if you take shear force at the point B, so here if you add FB is equal to sum of the forces. So this is RA and this is downward, so minus 12,000 into 8, then this is downward minus 10,000. So if you add, you will get to this value 51,750. So minus 51,750. Therefore, here plus 8,250 to it comes to down minus 51,150. Therefore, in between C and B, somewhere the point shear force value will be 0. So that is the reason why we have to find out this distance. Okay, from the C point. Suppose here to here 3 meter we know. So from the C point, from the D point, distance is X. We don't know. So here the shear force at D, FD is equal to RA minus this RA value minus this 12,000 into distance. If you convert this UDL from here to point D, if you convert the UDL into point load, this 12,000 into this 3 plus this X. Okay, minus again this because of this 10,000 Newton. So minus 10,000. So if you substitute the value in terms of X, you will get. So if you equate equal to 0, then you will get X value will be is equal to, okay, how much you will get? 0.687. So from C to D, the distance is 0.6875. So at point D, shear force is 0. There at point D, you will get the maximum bending moment. So at a distance of 3.6875 meter from the point A, you will get the maximum bending moment. Okay, so bending moment value out of bending moment at A. So you know very well it is the what happened? Yeah. So at point A, the bending moment value will be 0. You know very well, simply supported beam, bending moment A will be 0. Similarly, at B also bending moment value is 0. So at C, the bending moment at C means here in this point we have to calculate the bending moment at C. So RA load into distance 3 meter at point C, then download minus 12,000 into here you can see RA into this distance 3, then this minus 12,000 into 3 acting at 3 by 2 distance from here. So 3 minus 12,000 into 3 into 3 by 2 at C. Therefore, RA into 3 minus 2003 into 3 by 2. So you will get a moment at C. The moment at B, you know very well, that value will be 0. And moment at D. So moment at D means, so you know very well here, moment at D, this point. So RA into 3.06875, then this load 12,000 UDL, okay, and so this UDL 12,000, okay, into this distance 3.6875 into 3.6875 divided by 2, then minus of 10,000 into 0.6875. So if you calculate, you will get, okay, this value, moment at T value, okay. So here at moment at D, you will get the maximum bending moment value. That is nothing but this value, 11158593755. Okay. So the shear force changes sign between C and B. At the point D, shear force is 0. So bending moment will be maximum at the point D. That section model is Z equal to BD square by 6. So B into D is nothing but 2 times breadth given in the problem. So B into 2 times breadth whole square divided by 6. So if you substitute, we will get Z value 2B cube by 3. Then that is the Z value. You know the formula M equal to sigma maximum into Z. M value now we found, maximum value into sigma maximum given in the problem 8 into Z value you found now 2B cube by 3. Substitute. Okay, you can get the unknown value of B breadth. Then depth is equal to 2 times the breadth. Therefore, depth will be equal to 2 times this breadth value. If you substitute, you will get the depth also. This you have to calculate the breadth and the depth. Okay. So I hope you understand. Thank you for listening.